The probability distribution gives the probabilities of every possible numerical value that could occur in a phenomenon that has different potential outcomes with different numerical values. The unknown numerical value of a future outcome is called a random variable, denoted as x. So using this term, we can say that a probability distribution gives the probabilities of all possible values that a random variable can take. Let's look at some examples to see what I'm saying. This histogram shows the probability distribution of the random variable representing the outcome of rolling a die. This random variable can only take on 6 values, the integers from 1 to 6. In this case, there are only 6 possible outcomes, and each outcome has a different numerical value, 1, 2, 3, 4, 5, or 6. So the probabilities of the 6 possible values of the random variable are all equal. They're all 1 over 6, or 0.1667. This type of distribution where all x values have the same probability is called a uniform distribution. Here is a histogram of the probability distribution of the random variable of the sum of 2 dice rolls. This random variable can take on any integer value between 2 and 12, but there are a total of 36 ways you could get one of these 11 values. For example, there's only one way to get a sum of 2. That's if you roll a 1 twice, a 1 and a 1. So the probability of getting a sum of 2 is 1 out of 36. And it's the same for the probability of getting a sum of 12. There's only one way to get a sum of 12. That's if you get a 6 and a 6. So these two values, 2 and 12, have the lowest probability, 1 out of 36. There are 2 ways to get a sum of 3. You can get a 1 and a 2, or a 2 and a 1. And the same is for getting an 11. You can get a 5 and a 6, or a 6 and a 5. So the probability for the values 3 and 11 are 2 out of 36. So this is the whole probability distribution. The highest probability is for getting a 7, which is 6 out of 36. There's 6 ways you can get a 7. 7 is the mean and the median and the mode for this distribution. Here's another example. A company produces gadgets that each have a 10% chance of being defective, independent of other gadgets. What is the probability distribution for the random variable representing the number of defective gadgets in a pair of 2 gadgets? This random variable can take on 3 values, 0, 1, or 2, but there are 4 possible outcomes. None, the first, the second, or both could be defective. To get the probability of any of these 4 outcomes, we need the 5th rule of probability, the multiplication rule, because they're all joint probabilities. Since we said that the gadgets are independent, we use the simplified form P of A and B equals P of A times P of B. The probability of a gadget being defective is 10% or 0.1, so the probability of it not being defective is 0.9. So P of 0 is the probability of not the first times not the second, equals 0.9 times 0.9, which is 0.81 or 81%. P of 2, both being defective, is 0.1 times 0.1 equals 0.01 or 1%. And P of 1 is the combination of the 2 other outcomes, only the first being defective or only the second. So it's 0.1 times 0.9 plus 0.9 times 0.1 equals 0.18 or 18%. And of course the 3 probabilities add up to 1. So that's all for probability distributions of discrete random variables, where you can get a list of every possible outcome and its probability. Conversely, continuous random variables have infinite possible values, so you can't list them all. And their distributions, which give you all the possible values of a random variable, actually have infinite values, because the probability distribution gives you all the possible values of the random variable. So because these distributions consist of infinite values, you can't calculate their mean and standard deviation using sums, as you did in lecture 1, because they're infinite values. Instead, you need calculus to calculate these measures, which we're obviously not going to do in this class. Probability of any individual exact value is equal to 0, because it's just one out of infinite values. So if every value is 0, how does this distribution work? Each continuous random variable is described by its own probability density function, or PDF, which defines that particular distribution. How does it work? The PDF assigns a probability density, shown in the y-axis, to every possible x value, shown in the x-axis. And as you've seen in the lecture, when we introduced density plots, the probability of an outcome falling within a specific interval is given by the area under the curve of the PDF for that interval. Since the density keeps changing at every point, you generally need calculus to calculate an exact area. So when we introduced density plots, we were estimating. We were saying to get the area of, say, a width of 2 and a height of around 0.4, you just do 2 times 0.4. But this is 0.4 is an approximation because it keeps changing at every point. So you can get approximate areas, but if you want exact areas, you need calculus. And of course, the total area under the entire curve is equal to 1. To make sure you're clear about what a PDF is, it might help to refresh your memory about functions. This is a graph of the function f of x equals minus x squared plus 4 times 3 over 32, between the x values -2 and 2. You might recall from Algebra 1 that the graph of a function y, or f of x, which is the same thing, we're going to call it f of x. F of x equals minus x squared plus some constant is equal to such an upside down parabola. So like if x equals 0, then you have 0 plus 4 times 0 over 32. So you get this value here. 4 times 0 over 32 is equal to this value. If x equals 1 or -1, because you have negative x squared, both 1 and -1 are going to become -1. So you're going to have 3 times 3 over 32, which is this value here and here. And if x is equal to 2 or -2, you get -4 plus 4, which equals 0, as you see here. And for every value in between, you get all the values here in this curve. Now imagine if there was some phenomenon that had values ranging from -2 to 2. Let's say you had some weird kind of freezer whose temperature ranged from -2 to 2 degrees Celsius. And the probability distribution looked like this curve, with the highest probability centered around 0, and it tapered off to the sides just like this shape. Then this function, f of x equals -x squared plus 4 times 3 over 32, between -2 and 2, would be the PDF for that phenomenon. This function had to be multiplied by 3 over 32 in order for the total area to be equal to 1. Let's look at an actual real-world example of a continuous probability distribution. Let's say you spin a dial, and the dial could stop at any of infinite values between 0 and 360 degrees with equal likelihood. So because every possible outcome of infinite possible outcomes all have equal probability, you end up with a PDF that's just a constant function. It's equal to f of x equals 1 over 360, which is equal to 0.00278. So the graph of the PDF is just a straight line at the height of 0.00278. As we mentioned earlier, for the discrete case of rolling a die, this type of distribution, where all outcomes have the same probability, is called a uniform distribution. What's special about uniform distributions for the continuous case is that you don't need calculus to calculate any area. You just multiply the width times the height. So what's the probability that the dial stops between 90 and 100 degrees? The area under the curve between 90 and 100 degrees is 10 times 0.0278, width times height, which is equal to 2.78%. What's the probability that the dial stops exactly at 90 degrees? The area on the curve at exactly 90 degrees doesn't have any width, it's just a line. It's 0 times 0.00278, which is equal to 0. And we already know that the probability for an individual exact value is equal to 0. The most common distribution is called a normal distribution. It has this bell-shaped curve. A phenomenon that follow a normal distribution include things from SAT scores, human heights, IQs, weights of manufactured items like cereal boxes, and many, many other things. And this is the distribution that we're going to be dealing with for the rest of the course. Another important phenomenon worth highlighting that follows a normal distribution is the sampling distribution of the sample means. This is an amazing mathematical discovery called the central limit theorem, which we'll study more later in the course. But just to give you a basic understanding of it, if I take a sample of any shape, let's just pick this uniform distribution as an example. There are infinite values between 0 and 360 degrees with a delicate stop, which is why it's a continuous distribution. What is the mean of this distribution? For symmetric data, the mean is equal to the median. So the mean is 180. So if I take a sample of 100 dot spins, I'm going to get one here, one here, one here. And if I calculate the mean of my sample of size lowercase n equals 100, it's likely to be not too far from the mean of 180 because the dot spins tend to spread out approximately equally on both sides. But there's a small possibility that most of my 100 dot spins will end up on one side, and my sample mean will be here. And there's an even smaller possibility that my sample mean will end up here. It's even possible, though extremely unlikely, that every single one of my 100 dot spins will end up all the way here. And then my sample mean will be here. And of course, the same could happen on this side. There are infinite possible ways a sample of size n equals 100 could turn out, and each one has its own mean. The further and further out you get from the population mean, the smaller the chance, but it's still possible, that the sample mean will end up that far out. So what is the exact pattern or shape of the distribution of all the infinite possible sample means that you could get? The central limit theorem says that for any distribution, it doesn't matter what type of distribution, whether it's a normal distribution, a uniform distribution, or any other type of distribution, if the sample size is large enough, the distribution of the sample means will always look like a normal distribution. So what's the PDF for normal distribution? It's f of x equals 1 over sigma times the square root of 2 pi times 2.718 which this number is called e, as some of you probably know, to the power of negative x minus mu squared over 2 sigma squared. So sigma, which means the standard deviation, appears twice in the formula, and mu, which is the mean, appears here in the formula. So this means that every phenomenon that follows a normal distribution has its own unique normal distribution, depending on the mu and sigma for that phenomenon. So there are infinite different normal distributions. Now, every function that depends on x has to have x somewhere in the formula. So this is where the x appears in the formula. For every x value, you plug it in here, and you get a value for the function, and that's the density, which is the value somewhere here on the curve. So when x is equal to mu, then this x minus mu becomes 0. So this whole exponent falls away. And because this is a negative exponent, it makes the entire value smaller. So when this falls away, that's the largest value for the function. So that's why normal distribution is always going to be here at the center where the x is equal to the mean. Here in this figure, the mean is equal to 0, but that doesn't have to be the case. It could be anything. But whatever it is, the mean is at the center, and that's the highest value for the function. That has the highest density. And as the value of x gets further and further away from the mean in absolute value, which means to either side, to the positive or the negative side, this exponent gets bigger, and therefore the total value gets smaller, and it approaches 0 on both sides. So it never actually reaches 0, but it gets closer and closer to 0 on both sides when you're too far away from the mean. The mean in the formula only determines the position on the number line of where the curve is, And the sigma, the standard deviation, determines the dispersion. The smaller the sigma, the more peaked its shape is. So here you can see the blue and the orange are for mu equals 0, so it's centered over 0, and the green is mu equals 1, so it's centered over 1. But the green has the highest sigma of these three, so it's very spread out, and the orange has the lowest sigma, so it's very peaked. But this is only because these three curves are shown on the same x-axis and y-axis. If you rescale the x-axis to the y-axis, you get the exact same curve. So here you can see sigma 100 versus sigma 0.001, and they look exactly the same, but the x-axis and the y-axis are very different. The special case of the normal distribution, where mu is equal to 0 and sigma is equal to 1, and the formula simplifies to this, is called a standard normal distribution. What's special about the standard normal distribution is that since mu is 0 and sigma is 1, the values on the horizontal axis show how many standard deviations you are from the mean, which is 0. For the standard normal distribution, we call the values on the horizontal axis z-values or z-scores instead of x-values. So the values 1 and -1 are 1 standard deviation away from the mean. 1.5 and -1.5 are 1.5 standard deviations away from the mean, and so on. For standard normal distribution, you don't need calculus to calculate exact areas, because people have already done the calculus and we know the values. So here you can see 68% of the area is within 1 standard deviation from the mean, which means that 68% of the values in the distribution fall within 1 standard deviation from the mean, and which means that the probability of a random event that follows such a distribution falling within this interval is 68%. Now, why do I care about these values, since very few distributions follow a standard normal distribution? Because all of this is true for all normal distributions, not in terms of their x values, but in terms of how far away their standard deviation is from their mean. If you think of the 0 in this graph not as 0, but as the mean, and of all z-values as how many standard deviations they are from the mean, then all these facts about the areas are true for every normal distribution. For all normal distributions, 68% of the values fall within 1 standard deviation from the mean, 95% fall within 2 standard deviations, 99.7% fall within 3 standard deviations, and 99.99% of the values fall within 4 standard deviations. What if I want to know the probability for some other z-value that I don't have here? Like, what if I want to know the probability of a random event falling in the interval under z equals 1.35? So let's say this is 1.35. That probability would be equal to this whole area. What is this whole area equal to? Where do I get that? I said you don't need calculus. Everything has already been calculated. So where do I get those numbers? So there's special tables called z-tables that I linked to in the description. We can look up the area under the curve for any z-value up to 4 standard deviations from the mean. And like we saw, we don't need more than 4 standard deviations. So the way you read it is, first you go down here to the row that has the first decimal place of the number you're looking for. So let's say I want 1.35, so I go to 1.3, that's the first decimal place. But I want 1.35, so then I go here to 5. I can count 0, 1, 2, 3, 4, 5. And this is my number. This is my area under the curve for the entire interval to the left of 1.35, which is equal to 0.91149. So 91.15% of the entire standard normal distribution is to the left of the z-value 1.35. So there are 2 types of z-tables. The one we just saw is called a cumulative z-table, which whatever number you look up, it's going to give you the area on the curve for the entire area to the left of that value. So we found 0.9115 for 1.35. The other type of z-table is called a 0 to z-table, and that gives you the area under the curve from 0 to that number. So if you look up 1.35, it'll give you the probability of the value falling between 0 and 1.35. It's very easy to convert between these two tables because the only difference between them is this white area here, and this white area is just equal to 0.5. It's just half of the total area. And you can see that this value is just 0.5 less than this value. But it's important to know what z-table you're using to know what the value it's giving you means. If you want the probability that z is greater than 1.35, so that will be this white area here, for this z-table, you just do 1 minus this value, and you get this value. Because we know that the whole thing is equal to 1, so this area is just equal to 1 minus this area. And for this table, because we're only working with this half, you just do 0.5 minus this value, and you get the same value. Also, because the bell curve is symmetric, the area between 0 and 1.35 is equal to the area between 0 and negative 1.35. So for this z-table, whatever value you have for positive numbers is the exact same area on the curve for negative z values. And for this type of z-table, the way it works is that the area to the left of 1.35 is going to be equal to the area to the right of negative 1.35. That will be the mirror image of this image. Now generally, the data you're interested in doesn't follow a standard normal distribution. So what do you gain out of these z-tables? You convert your x value into a z value using this formula, z equals x minus mu over sigma. And then you could just look up your area on the curve in the z-table. Or if you need to convert from z to x, you use this formula, x equals z sigma plus mu. And this will become a very important part of the rest of the course. At the end of lecture 2, we mentioned how probability and proportions are two sides of the same coin. We've now seen 3 ways how this is the case. The first is the idea we mentioned at the end of lecture 2, that frequency distributions of observed data follow an underlying probability distribution, like a normal distribution. And this relationship between the relative frequency of observed data and probability is known as a law of large numbers. It says that the larger the data set, the closer the relative frequency distribution will get to the theoretical probability distribution. And for very large data sets, the relative frequency is equal to the probability. In other words, the likelihood of the value you will observe is equal to the proportion of the values you actually observed. In theory, a dataset can never become so large that the proportion should exactly equal the probability. But with very large datasets, the difference is so small that it's undetectable, and we just say they're equal. The second way probability and proportions are two sides of the same coin is just the basic definition of probability. Probability is just equal to the proportion from the population. For example, if you have 5 marbles and 3 of them are red, then the probability of picking out randomly a red marble is 3 over 5. So probability is just equal to proportion. And this has nothing to do with population size. It's true even for very small numbers. The third way proportion and probability are two sides of the same coin is the same idea as the second way, and it's what we just seen in the previous slide, that the probability of an event falling within a certain interval is equal to the proportion of the distribution or the area in that interval. Because we designed the total area to be equal to 1, it happens to be that proportion is equal to the area, because the total is 1, so any value divided by 1 is just equal to the same value. So that's why we just say that the probability is equal to the area. But fundamentally, it's about the proportion of the distribution. That the probability of an event falling within a certain interval is equal to the proportion of the values in the entire distribution.